Thanks for coming. Quick question. How many people run something on the JVM here? All right, so most of the room. Just regular Java, raise your hand. Scala? Cool. So this talk is called Fun with Clojure. As Carmen mentioned, I do a little Clojure. It's mostly for fun projects or like tooling and stuff that I have to use or teammates have to use. So this is on the 21st century language track, so I figured we could do a little history lesson at first. So what is the 21st century? It's anything after January 1st, 2001. So Clojure made it in there. So it is a 21st century language, even though it's been around for some time, since 2007. Lisp, which is what Clojure is, was specified firstly in 1958. CSP, which is communicating sequential processes, was described in 1978. The JVM first was introduced in 1994. JavaScript in 1995. And Clojure, right? So Clojure leverages all these technologies from back in the day, and it's putting them together to solve problems that we're currently having in a very pragmatic and simple way. So 21st century problems, what are these? So we probably want some evolvable systems. So we want to quickly add features for our customers, for making money, because that's how we get paid. We want to refactor our apps, get rid of technical debt, but we want to do that with confidence. We want to have some resiliency, so Clojure allows you to have an open system, just because it's a data-first language. And you probably want a quick service, right? So low response times and very responsive services. And then most likely you have to do something with JavaScript, because that's just the way of life. So our journey today, so I will be your guide through Lispland. For some reason, people get really intimidated when they see parentheses, even though it's not that bad. So I'm here to guide you and show you the way and answer any questions that you might have about it. We're going to talk about 3 concepts, and hopefully one of these concepts, so all of these concepts, will spark your interest and you'll give Clojure a try. This talk is basically 3 talks condensed into one, so we'll see how that goes. So the agenda, we're going to talk about specifying our problems and our data for correctness, and then we're going to talk about concurrency and parallelism, and then we're going to touch on ClojureScript, which is the JavaScript part of the talk. So a little bit about me. My name is Jearvon, as Carmen said. Day to day, I'm a developer advocate at Comcast. Surprise, surprise, we have one of those. On Twitter, you can find me if you want to ask me questions or get in touch with me. And then the code for this talk will be on GitHub for that URL, and we'll publish the slides later, and you'll get access to them. So why did I decide to give this talk? So as I mentioned before, my day-to-day is just building tools for folks and getting them unstuck on certain problems. And I've been recently trying to write a policy as code engine for AWS. I'm trying to do that in Clojure. And I found happiness again with Clojure, and I was like, I should share this. So that's where this talk is coming from. And Zishan, who works with me, knows about this challenge that we currently have. So what is Clojure? A little synopsis. Clojure is a dynamic language, so it's not statically and compiled. It is a Lisp. It's predominantly functional. It's a very pragmatic language, so it's not going to force you to be one way or the other. When you want to be functional, you can be. When you want to get away from that, you can also. It has immutable data structures, but also you don't have to use immutability all the time. Functions are first-class citizen, and so is data. Clojure really focuses on simplicity. If you watch any of the talks from the author of Clojure, Rich Hickey, there's always something about simplicity in one of his talks, so I highly encourage you to check that out. So just enough Clojure. So how many people are familiar with Lisp? Cool, so most of the audience. So for those that are not, this is basically just enough for you to figure out what a Lisp is or how Clojure works. So you have two parentheses, so an open and a closing. The first thing in the parentheses is always the function call, and then the rest of the things can be considered as arguments. So this is how you would add two numbers. So the first one is the addition operator, and then you pass in two arguments, and you would get 3 out of that. Some other Clojure things that you need to know for the talk is Clojure separates code into namespaces. So similar how you have a Java class, you'd have a namespace in Clojure, and you could import that namespace using similar to how I have it here. So you say require, and then you could alias it, so you don't have to use the fully qualified name at all times. And then you could call the functions in that namespace using the alias that you give it to. So here we're saying require the spec namespace, and we're going to call the valid function from that namespace. And that's going to be available in our QCon spec core namespace. So what is spec? So I'm going to try to get through the first part of this talk without mentioning types. If you are a type enthusiast, I ask that you open your mind and you get past that this is not like static types, but it is still useful. So types allow you to describe data. It allows you to have documentation without writing docs because you're specifying functions, you're specifying data. Sometimes you come back to a function like 3 months from now, or you're trying to change some code later, and you're like what's the signature of this function, or how does this work, or what is it supposed to return? Or sometimes you have a higher order function like a map, and you're iterating over a data structure, and you're like, what is in this data structure? I don't know. So when you're code reviewing, you're kind of lost, and you have to go ask the person. So this is the anatomy of a spec. So similar to how we saw the list code earlier. There's a spec function, which is like valid. There's a predicate, and there's a value. So this is what a real-world spec looks like. So the valid is a spec function. The int question mark is a predicate. And the value that we're passing in is 3,000. So this is basically saying, is the number 3,000 an integer? It is, so it's going to return true. So the signature of a predicate is any function that takes in an argument and returns a Boolean value. So it could either return true if it matches the criteria, or it returns false if it doesn't match the criteria. So spec was introduced maybe a year ago, and any Clojure already has predicates in the language, but they introduced some new ones, and these are some of the predicates that you will run into. So if you want to test if a URL matches the URI, that's built in. You don't have to write that yourself. You can check if a number is even or odd. And we'll see some predicates later in the talk. And then you could define your own predicate. So this is a predicate that checks if someone is legal age for voting. I don't know why I did that, but voting was in my head at the time. So it says it takes in an argument, which is the value, the thing you're checking against if it's above 18, equal or to above 18. And they will return true if it is, false if it doesn't. So far we've just seen how you would just use specs on demand, right? So you're in a function, or you're just writing them ad hoc. But similar to programming, you probably want to give them a name or reference them later, and you don't want to rewrite the same spec. So that's where name specs come in. And here you can see we're creating a port spec, and your port should be an integer, depending on your service that you're writing. So let's go into some code. So in this talk, I wrote a lot of code, and I'm going to try to do some live demos. But there will be some switching happening, so please be mindful or have patience. All right. Okay, so can everyone see this code? All right, so it is not a requirement to use Emacs if you're writing Clojure, but I highly recommend it since it's the best editor ever. Just kidding, just kidding. All right, so here you can see we're requiring a bunch of namespaces. Most important ones are the spec namespace, which you saw earlier. And then later on, we're going to talk about the gen namespace and the test namespace. So basically, I'm just going to evaluate this stuff. You see, we're just checking it in real time. Basically, what we saw earlier, and this is our custom spec that we wrote. So that's 15. If we want to change that to 21, that's the number you're checking against, will be true. And this is the spec that we wrote. That's a name spec. Cool. I'm just going to wing it and not do notes. So this is the name spec, and then this is how you would reference the spec later on. So you're saying, hey, does this thing match the port specification? And what is a port specification? It's an integer. So you can basically reuse this in all of your Clojure code. And then when you put a name spec, everything goes into this global registry. So you can reference it either in your front-end code, your back-end code, or any of your namespaces that you're requiring them to. And the patterns that I've seen is like some people have it just a giant spec file that has all their specs and the specs all their data out, or they have it per component or per part of their application. So if you have like a database component, all your specs for your database and your data lives in that database. So now that we have a name spec, Clojure code really makes high use of maps. Clojure really likes your data to be a first-class citizen, and they don't want you to hide your data. They just advise that you pass around basically a map data structure, a vector, which is just an array with the data in it, and then you could modify it or read it however you want. They don't want you doing any data hiding like how you would do in Java and get getter methods and setter methods and stuff like that. So you probably will be speccing maps a lot. So in your code, you probably have a config file, and I'm sure many times you've launched your application and you don't have the right config and you can't figure out why the application is not working. And you don't have any code doing error messages on your config. So we're going to write some code to specify what a config for our application will look like. And our config just has a port and has an environment. So the port is going to be an integer and the environment is going to be a string. So we're going to say, hey, let's define a name spec called config. It's going to be a map. That's how you know it's a map because it has the word keys in it. And then we're going to say, we're going to require that the key be port and be env, and they must be in the config to be a valid config. So one of the magics here is you notice that we're not saying in the config spec that what the values of the port or the env should be. Basically, we're starting from the smallest construct that we want to use, which was the port, and then we're going to build up larger data structures from that. So when Clojure reads this config and it wants to do validation against it, it's going to hit the port keyword here, and it's going to say, what's the definition of a port? And it's going to go back here and say, okay, it's an integer. Is it an integer? Yes. And then it's going to go to the env and go back to the definition of that. So you can basically reuse the definition of port in other places. Like if you have a specific Postgres config, you could use the port definition that you had earlier in there in another definition of a config. So you might be wondering about port. So a port is not only an integer, right? There are other rules for ports. And basically, this is the way you solve that is composing specs. So specs are composable. So here you can see that you're using the two specs. So I define a new spec called port range. And those of you who are familiar with ports know that there's a highest number that you can get to, and there are some reverse ports that you should not be using for your application. So I'm going to say, hey, the port that you specify for me should be 1023, and should be above 1023, and it should be lower than 65,000. Now, if you require that your app run on, say, 3,000, you could say that the port number should just equal that instead of giving it a range. I'm only using this to show that you can compose them here. And this is a custom spec that we wrote. The hashtag there is just a fancy way to write anonymous functions. And the percentage sign is just the arguments that you're passing in, which is the port value that you're specifying. And then the second part of this is we're saying, okay, a port is these two things. And the and is how you would say that it should match both of these. If it should match an either or, you use the or keyword. So you're saying, hey, it should be an integer, and it should match the spec valid port range. So let's do some more demos. We'll talk about what you can do with spec. Also, if anyone knows the shortcut on how to do mirroring displays, let me know. Okay. So back to the best editor ever. Sure. Okay. So I'll make that smaller. No, you can't see. Sorry. Oh, I have to mirror. Cool. All right, now you can see it. Okay, so here we have a port, we have an env, and you can see we're also composing what an env should be, right? So it should be a string, and it should not be blank. And we'll see why we want to specify a blank later. So you have a config. We compose some stuff, and this stuff is already loaded. So what can you do with specs? You wrote these things, how do you use them? So you have three options. You can do validation against them, you can conform them, which just means that you're going to take the data that you're getting in and conform them to some type of map structure. So if you're getting random data from your config file, you're going to conform that into a map that your configuration function could use. So let's look, you already saw what validation looks like. So we're going to do some conforming stuff. So here, we specified a building spec and an address spec. So we say a building is going to match a series of numbers, the building number, and the address is just a string. And here we're going to conform this array data structure to that map. So you see it printed out the result of that, and it's going to give me back a building number, which is the first value of the array, and then the street address, which is the JFK Boulevard. And we're getting those keys from this cat value here, which is basically, you can think of this like if you have an array of arrays and you need to parse that into a data structure that you can read or use in your function, you can just use conform for that. All right, so let's look at how this would be used in a function. So here we have a load config function. It takes in a config, it tries to conform it. And the result of a bad conform is an invalid value, and the result of a valid conform is just a conformed value. So we're going to say, hey, is the value of conformed invalid? If it is, throw an exception and give me exactly why it failed. If it's valid, just return that value. So we're going to call this function with a data structure here that we have. So this is what a config that looks like that we're passing in, and this should be invalid. So we're going to see here that it says spec failed, that was the value. It should have had an env key, and the env key is this basically predicate. It should be a string, and it should not be blank. So we're going to go back, and we're going to try to load the config here for this valid config. And it should just be a success. It just returns what the map should be. Does that make sense for everyone? Cool. So in here, you see that in this line, we're calling this function call explain. And that's another thing you can do with your specs. You can explain why they're failing. So there are these functions called explain string, explain, and explain data. We're just going to evaluate these and see what they look like. So it just gives you a nice evaluation of why that thing is failing. So you can see the value of this is like when Clojure is a dynamic language, right? So you don't have those compile time checks. But at runtime, you get this nice output and this nice validation and checking. So another cool thing is, so this spec matches should fail for one of the compound specs. And you can see that we are getting a nice output here of why. It's basically, you can see it's saying, it's giving you why that's failing, right? So it's saying it's less than the invalid range. Another thing you can do is get documentation. So I'm going to evaluate this. Hold on, sorry. Live coding. So let's evaluate this and see the output of it. So here you can see that if someone wants to know what a port is when they're coming in to work on the app later, they can just come in and say, what's the docs looks like for this? And then you don't have to write any docs, right? It's just going to show you what the spec is. So everyone who hates writing documentation, this is a great tool for you, which is most of us. All right. Let's go back to the slides. So we went over what you could do with spec, right? So far we've only been specking data that we're getting in or data that we're passing around, but you could actually spec your functions. And here you can see we're specking a find by ID function. So just a raise of hands, let's do a survey. If you have a find by ID function and it doesn't find anything, should it return nil or should it return like a null object? Raise your hand if you should return nil. What would you do? Nil? All right. There's no right or wrong answer. It's just preference. And raise your hand if it should not be nil. It should be like an empty object. Okay, cool. Just a fun question. All right. So let's try to spec out our function find by ID. So you might think, so a situation could be, okay, you have to write this function. It's like a new card you're taking from Trello. You give the function some thought. What will it take in? What will it return? So here we're going to use the fdef function. We're going to call find by ID as the function name. We're going to say there are three things that you could spec a function with. First is the arguments. So we're going to see what are those function arguments. So in functional programming, you usually pass in all the things that you want to use. So you're going to pass in a database. For this situation, we're just going to use a map. And then we're going to pass in an ID, which should be a valid ID. And for spec, for a valid ID, it should be greater than 0, because you don't have IDs that are 0. You don't have IDs that are negative numbers. So that's just a custom spec that I wrote earlier. And then it should return a map. There's a bug here. We're going to discuss how to solve this bug later. So once you define the spec, you define the function. And it's basically what was in our head when we were thinking about it. So find by ID, it takes in a database, it takes in an ID. It will filter that map until it finds an ID that matches it, and then return the first value from that, because it's an array. So let's go back to some code. Do this whole dance again. All right. So this is the database. This is the ID spec. It should be an integer. It should be greater than 0. And I also started specking out the what the map should look like, right? Because not only should it be a map, it should be a collection. So the database should be an array, and it should be a collection of maps which match this person map. So here, we're saying a person is just a map with an ID in it. The optional thing is a name, which we're not specifying. And then a person DB is a collection of the person spec, and the kind should be a vector, which is just an array in Clojure, and it should be distinct. So we don't want our database to have multiple maps with the same IDs. It's going to say, like, make sure it's like 1, 2, 3, 4 instead of like 1, 1, 2, 3, 3, stuff like that. So we can see how Conform works there. So here we have a DB, just var that has a name. It has two options in it. One is me and one is Beyonce, because I know Beyonce on a personal level. Just kidding. We're going to see that conform. So we're taking the first value and say, hey, do you match what a person spec is? And it says yes. And then we're going to conform the actual DB var. And that's what it is. It does match. And this is the spec definition. So here in this definition, we actually have one more line. So here we see the args, and we're saying, hey, these are the args that we expect. And then this fn keyword is going to basically run a function on the return value. So return, the RET keyword just matches the type on the return value, but the function keyword actually runs any type of custom validation that you want on the actual return value of the function. So here, we're saying the ID that we pass in, which is the ID from args, which is this value right here. So this value, which is the argument, should match the ID value of the return keyword. So you're basically saying, hey, if you ask for a record with a 1 ID, the return value should have the ID of 1 in it. So you're doing like a equal matching. So if someone, you could think of a situation if you were testing this and you forgot that you hard-coded the ID in the function, it would catch it, right? And this is the implementation that you saw earlier. So we can see, we'll just execute it. It returns nil. It's not what the thing should be, right? We're going to fix that later. OK. So we saw how we could spec out functions, how we could spec out the data that we're seeing. What can we do with those things? And the next level to this is doing generate exploring. And you do that using generators. So how many people, did anyone go to the property-based testing yesterday talk? So this is what that gets into. So here, if you recall earlier, our config spec, if we wanted to see the shape of that data, we could use the generator, the generate function from the generator library and execute that. And I'll give us an example of what that looks like. So you see it has a port, it has a random port, and it has an end and a string value. If we wanted to see how, if we generate a lot of these, if it does match up and there are no errors in it, we could use the sample command, which is 10 at a time. And you'll see a better use case for this later. So here you see just 10 values of what an example config should be. And if you wanted to put more restrictions on saying like the M should be at least 3 letters, like prod, or 4 letters, like prod or stage, you can set those up in custom generators. You could also exercise the function, which basically runs the function many times and then gives you the return value of it. So if you look down here at the last value, it returns ID 1. And before the closing parentheses, you see it's requiring the one ID. You could also instrument functions. So we're going to turn that on, and we're going to say, so this is what all right, so we turned on instrumenting, and we're going to pass in a string, and this should yell at us. So it gives us a nice error message, depending on your definition of nice. But it's going to say, hey, you pass in the value of 57, but that should actually be an integer. So it failed that spec. So you can, if you're running your tests and you're doing, you're writing a test against this and you pass in the wrong values, instrumentation could catch that. Or if you're in production and you get a wrong value, you know. So if we did that, 57, that error should go away. Cool. And you could turn this off with unstrument. I don't know why they didn't call it uninstrument or use a better word, but unstrument. All right. So going back to property-based testing. So when you're using Spec, Spec knows about the data that you want and you don't want, right? So you can imagine a scenario where you're able to generate a bunch of random inputs, give it to your function, run it, and it could find possible scenarios that you didn't match up to or didn't protect yourself against. So we're going to call this check function. We're going to run it 1,000 times and try to find a value that does not match our function spec. So run that, and you can see that it immediately finds one, and it says, hey, if you pass in an empty array which is this value here, and the value 1, it does not return a map. It returns nil, and it should satisfy map. So let's see if we can fix that. Does anyone want to give it a shot? So earlier, I wrote a spec that already does this. Let's just run that. So this is some complicated code because it has a lot of parentheses, but don't worry. So earlier, we all agreed that nil is a valid value. So we're going to just modify our spec to expect nil when it does not exist. So we're going to say, if there's not a value from return, then nil is valid. If there is a value, then 1 should match up into the map. Sorry, this is the line where it says, if there's a return value, then map should be a valid output for the return value. If not, then nil is fine. So nil question mark just checks the return value. If it's nil, it will return true. And then this function below here is just doing more checking, saying when it does find something and it is a map, then the value of ID should match up the ID that you passed in. So let's run that again. And try to find a value. So sweet, it's a success. So we fixed our spec and our function. Let's see if we run it maybe 5,000 times, what happens? Success again. So we wrote a perfect function. All right. So that's the end of spec. I'll pause for questions around spec for like 2. If there are questions, I'll pause. So any questions around spec?
I've used it a little bit before, and it was always confusing about whether instrumentation was actually turned on or not on a given function.
Okay. I don't have a, you mean to check if it's instrumented or not, if it's turned on for?
When I'm developing and evaluating expressions, I wanted it on all the time.
So there is an instrument-all that just instruments all your functions. I have also Googled this, and it seems like some people write custom functions to only instrument their stuff that they're writing, because I don't know what the repercussion of instrumenting all functions would be.
Yeah, I was kind of hoping there was something like have it on for everything during dev.
Yeah.
And then turn it off for everything.
Well, you can set up your Lanigan profile in developer mode for it to run the instrument all, and that'll instrument all the functions. So it's just instrument-all.
Is there a use case for spec beyond generative testing, or is that the main use case?
I mean, it's one of the biggest value, but I think if you use Clojure, you know that, well, you'll quickly figure out that you have all this data roaming around in the maps, and you could spec out only the data that you need and then just not crash your system for inputs that you don't need. So the Conform spec just helps you with that, just fetching the data that you like. Any other questions with spec? Also, I should repeat the questions. Sorry. Okay, so you can ask more questions later, but we're going to jump into the second part of the talk, which is concurrency and parallelism. So this is a quote from one of the Clojure books, Clojure Applied. And it says, the future belongs to languages that can automatically leverage more cores as they become available. And most of the talks at this conference this year sort of mentions this, and anything that you read, it always talks about concurrency, right? The languages that are doing well at this are languages that people are adopting. So Clojure being a very pragmatic language, they don't want you mucking around in the lower level stuff with concurrency and stuff like that. So they provide you higher order functions to basically deal with this stuff. All you have to do is use a function, and you can trust that Clojure is doing the hard and heavy lifting for you. I guess we should define concurrency and parallelism. Does anybody want to give it a shot? Parallelism is things that you can do, multiple things that you do at the same time. So you can think of like if you're taking the train home, there are like 4 cars and 4 doors. So we're entering the train in a parallel manner. And then the concurrency part of that is the line that we're forming to enter the train. So, you know, Amtrak has done this great, well, not in the Penn Station, but we form a line, and then we use all the train car doors to parallelly go into the train or board the train. Okay, so Clojure runs in the JVM. That's one place that it runs. So if you're comfortable with Java or the JVM, you don't even have to use the Clojure stuff. You could just use your old Java ways and just use the things that Java gives to you. If you do want to take the benefit of Clojure, you can. So why is concurrency great in Clojure? There are 2 reasons why. First is pure functions. So Clojure encourages you to use pure functions, right? So a pure function is just a function that doesn't have a side effect. So you can imagine that if you were saying like, I'm going to concurrently or do this in parallel, but I'm also like writing some value, then if you're doing that thing over and over again, you're having side effects, and that's not good, right? It's having an effect on your system that you're not expecting. So when doing this type of work, you should use pure functions, small pure functions. And then the other part of that is immutable data. And by default, Clojure provides immutable data structures. So here you can see that we're using the assoc function. I'm associating my last name into this map, and it's going to return a new map with my first and last name in it. And the second thing of that function is me doing the same thing by returning m, and m will still be the function that I'm going to use. So I'll show this in a little bit, live coding. And there's this other thing called an atom. So I keep saying over and over that Clojure is very pragmatic, and they want to help you in whatever way they can. So they also recognize that not everything could be immutable, right? So you need to have some state mutation. And one of the most popular ways to do that is using the construct called an atom. And this is an atom. And what an atom allows you to do is just have a like global variable basically, and have a safe way to mutate that using the swap function. And the swap function is an atomic function, so it's going to say, so a scenario would be, okay, I need to update this variable. Let's say 2 threads are, actually let's just show the code. Okay. So let's find the code. All right, so let's show the immutable side first. So here you see that even though I'm associating inside of the function my last name, it's still returning the original map that I had. So it's not modifying it. So you could expect that in the background, when you're relying on something, some data structure, something else isn't changing it. It's always the value that you set it to be. So I wrote this little situation here, a scenario, where we're going to say it's a green smiley, because we're all going to vote green when you leave the room. And it's an atom, and it's set to 0. So the situation here is, let's say we have a server. It's going to reach out to all of the little boxes that has the values on them, and it's going to basically increment the value on the counter. So the counter here is the green smiley. And if we run this, it's going to run. It's going to spin up threads for each one of these and increment the value. And the way you get a value from the atom is doing a dereference. Well, hold on. I ran that earlier, so I'll reset it to 0. Basically ran through all these examples. So it's going to do that, and then it should be 9. So it's safely in the background. All 9 threads are writing to this value. And the way it does this is a check and set. So if a thread tries to write to the atom, it'll make sure that it's the most updated value that it's getting first before it overwrites it. So that's where pure functions come in, right? with the check-in set, it's going to run it multiple times to make sure it's getting the right check-in set. So if you have a function with side effects, then you're just going to do haywire on your system. So that's an atom. I'll just stick with the code for now. So here we have a simulation of a slow square function. What it does is just multiplies the value that you're passing into it, and it's going to sleep for 1 second. So right out of the box, if you want to make your system faster, Clojure has this higher order function called map, which does things in sequential manner. But they also have pmap, which does a thread for each item in the collection. So sometimes pmap is not worth it. So with an array of 3 values, spinning up a new thread for just 3 values, you're going to have more overhead in doing the thread manipulation than if you were to do it sequentially. So we're going to open up our REPL, and we're going to see some timings on these. So first of all, we're just going to get a time. So to increment these 3 integers, it's 0.03 milliseconds. For pmap, it should be a higher number, 30.32 milliseconds, because it's doing the thread manipulation behind the scenes, so it's not worth it here. But it'll probably be worth it if you were trying to hit a slow service, right? So let's do a map over a slow square. So you can see in the background it's running. It's going to print out a time soon. So it's 10 seconds, basically because there are 10 things in the collection. Each thing takes a second, so that number is right. So let's try. Does anyone want to guess what the parallel version of that will be? The time around that? 1? Yeah. Yeah. So it's running. It comes back to be 1 second because it's just, the longest time will just be whatever the longest thing takes to execute, right? Because it's doing 10 threads, and each thread takes 1 second. So that's the first thing. One scenario of this is I wrote a bot in Clojure to go pull requests from GitHub to put in our Slack channel. And for each repo, I just parallelly hit the GitHub repo and brought back the pull requests. I didn't have to do any hard work. It just came out the box. So here, the other construct that they give you is futures. Java also has this, but it's easier to use here, right? All we're doing is using the future function. That's going to create another thread and run it in the background. So we have a fake scenario here. We have 3 services that we're going to hit that builds up 1 object. So we have a recommendation service, an account service, and a device service. But one service takes longer than the other. So again, the longest that this thing will run in parallel will be 5 seconds. So I have two functions basically doing the same thing, except one does a future, again, which does the stuff in the background, and then one which does it sequentially. So let's run the sequential one first. Whoops, hold on. Have to evaluate that. So it's running, it's running, it's running. It'll return soon. Imagine if this was a user using your service. You don't want to do this, right? So it took 11 seconds, which is about right. We're going to call build result, which does the future version. And you see it takes 5 seconds because it's doing it in parallel. So one of the benefits of this is like, you don't really have to give this any thought, right? Because you have immutable data structures and you have these higher order functions or high level functions that you could just use and have safety with your code. I have 5 minutes, so I'm going to rush through some other things. Okay, so let's talk about reducers, and then we'll talk about CSP, and then we'll be done. Okay, so earlier you saw the map function, right? And if you have maps, maps just do that in a sequential order. Now you have these reducer functions, which Clojure also provides. So let's take this as an example. So here we're filtering the rides. We're going to map over them and get the ride count out of them, and then we're going to reduce them. And a reducer function is just something that takes a collection and reduces them into something else, into one value. So here we're just reducing them into one integer. So if we run this, this will first pass and rise into filter. It will filter those, create a new collection, then it will map over that collection, and then the reduce will reduce over that collection. But there's, you can imagine that if you have a big value, if you're creating like a large array, you're constantly creating these objects, and that's going to be slow, right? And there's going to be a lot of garbage collection. So Clojure has this idea of reducers, which basically composes that chain into one foldable function. So you're not creating those intermediate arrays. It's just going to do it all at once. And then there's this fold function that basically runs that foldable in parallel. So here you can see, so this one cool thing about Spec again is I'm using Spec to generate 2 million samples of what our driver map should look like. And then I'm going to use that data in this function. So let's open up that. Okay, so let's run the timing on the sequential version. And you can see it's 368 milliseconds. And then the foldable version, which runs in parallel, is 234 milliseconds. So it's like more than 100 seconds quicker to do it versus the foldable way. Okay, and then the last thing we're going to talk about, since we only have 5 minutes, is core.async. Which if you want to talk earlier, or if you went to Carmen's talk on the CSP paper, you should check that out. So core.async is Clojure's implementation of CSP, which could be boiled down to just communication via processes. So one process sends another process a message over a channel. And if you use Go, Go also has Go routines, which is based on CSP. So how many people have heard of the token bucket filter algorithm? Cool. So I'll explain it. So all it is there's some rules, right? So there's a bucket, and your bucket has a certain amount of tokens in it. Let's say your bucket has 10 tokens. A value comes in, so this is the rule for the buckets. And there's a process writing to the bucket, right? So it's writing tokens constantly to the bucket, but there's a max amount. So if there are 10 tokens in the bucket and 10 is your max, the process should stop writing to the bucket. Then there's another process that's receiving the token bucket came out of packet routing, so it's going to send a packet. If the packet is the same size as how many tokens are in the bucket, then the packet goes through. So it's basically a rate limiter. But you could apply this rate limiting to other things like appointments or whatever. So this problem fits with core.async and CSP very well. So first, we're just going to define the bucket, right? And the bucket is just a channel here that we're getting in. So someone's passing us a channel. So let's see what the definition is. So we're going to pass in a token bucket. We're passing a value of 15, which is the maximum amount of tokens that we have. Now, when the way you put stuff on a bucket is using these put functions. So you're going to put. When the channel reaches its buffer size, it's going to stop writing to it or stop accepting values. So we've just defined the bucket with like 3 lines of code. Okay. Like 2 more minutes. So that's our bucket. So you see here, we're going to put a value on the bucket. This is the bucket. Or we're just going to put the t value. We have this other channel construct called a timeout, which is times out it waits 1 second and then it closes itself. So we're basically simulating a 1 second delay and then writing to it again. And this is the limiting part of it. So basically we're saying, okay, what's the packet count when it comes in? We're going to get the size of it, and we're going to take it off the in channel, and then we are going to check if the bucket has enough tokens in it, matching the size. And then we're going to extract that amount of tokens from the bucket, and then we're going to put on an out channel, which is basically listening. You could think of that as your processor, that the packet was processed. So we can see that here. So earlier I started up this function. We're going to pass in, 1 second. Start that function. We're going to send a message, and it has a size of 12 on our inbound channel. So you see we saw packet process, so we just stole 12 tokens, right? So there should be less tokens there now. So you see we got the waiting on tokens message. It's going to keep checking, and it's going to keep writing to the bucket. And when there's enough, it automatically just sends that message to it. So it's basically just a different way of, if you were to talk earlier about Elixir and OTP, it's basically the same concept, just message passing between processes. So yeah, that's pretty much concurrency. We will not go over ClojureScript, but it is cool, trust me.